portion is e raised to a function. When I differentiate this, I do have a differentiation rule for this, which is e raised to u multiplied by u prime. There is no need to apply natural log to this. Now, if I have 2x plus 1 raised to 1 over x, I do not have a rule for this. Not possible without natural log or log, doesn't matter, normally natural log. Okay, so this is not possible without, we don't have a formula for this, but we do have a differentiation rule or a formula for this one. So we do not apply, in this case, natural log. So, okay, so let me get you started on this problem and then I'll wait for another minute. Okay, so we're asked to determine absolute max, absolute min, and I will also say which one is local on a closed interval. When I'm asked to find or study a function on a closed interval, I have to find its derivative. I have to find the critical numbers. I have to find the sign of the derivative, and then find the value of the function at important points, critical numbers and the endpoints. So now let's differentiate this function together. So f prime, this is a product of two functions. I differentiate x. Is this blurry or is it clear? Because from my angle it's a little blurry. Okay, perfect. So the first function prime is 1 times the second function plus the first function times e to u prime, which is e to u times the inner function prime, negative 2x over 8. This is it so far. Any questions on this problem? Nika, are you okay with this so far? I didn't get the chance to look. Forgive me. Okay, so then, of course, I'm going to simplify the 2 with an 8, and I get 4. Of course, I will factor out e to negative x squared over 8. Remember, factoring is crucial in these derivatives. From the first term, I have 1. This is out. I have negative x over 4 multiplied by x. It's negative, so I have negative x squared over 4. Are we okay so far with this? Is this clear, everyone? Okay, so now I have to find the least common denominator, which is, yes, so it's 4. And I have 4 minus x squared. And now I can bring this down if that's what you want. That's fine. Yes, I will factor out negative 1. And I will factor the numerator. How? Good. X minus 2 and x plus 2. Perfect. Why do I do all this? Because this is all the prep I need in order to find what? Perfect. So there are two possibilities. F prime being 0 or f prime being undefined. Somewhere. That's not the case because this is never 0. No critical numbers come from f prime being undefined. But there are two possibilities for f prime being 0. Can anyone give us those possibilities in which f prime is 0? Perfect. And the numerator is 0. X equals 2, x equals negative 2. Now I have to go back to my table. This one doesn't fit. It's fine, but it doesn't fit in the interval I was given. So I can only plug in 2. So 2 and 0. I have to immediately determine these numbers. the y-coordinates of those points. I put the function in the graphing calculator in y equals, clear what you have. So it's x e in parentheses negative x squared divided by 8, close the parenthesis. And with table, second table, I need -1, 2, and 4. -1, 2, and 4. Finally, he's here. Okay, so -0.88, 1.2, and 0.54. Now you can say this is already clear. Yes, it is. However, I have to study the sign of the derivative just to make sure I didn't make a mistake. So let's study the sign of the derivative. I'm going to plug in 0. 0 is on this side of 2, 0. So 0 here, negative with negative of a positive. Negative with negative of a positive. This is always positive. E to the x is always positive. So what is the sign to the left of 2? I plugged in 0. This is 0. I have -1 times -4 over a positive number. Positive, right? I have -4 times -1 over a positive number, correct? So now let's plug in 3. If I plug in 3, I get 9 minus 4. This becomes positive. This is always positive, but there is a minus in front. Negative. Now I check my work to make sure that this row works well with this row. So from -0.88, it was negative, yes, to 1.2, what does this function do? Correct. Is that supported by the sign of the first derivative? And then from 1.2 to 0.54, what does this function do? Okay, and it's supported by the sign of the first derivative. So all I have to decide now, you don't have to do this, I just want to explain. I'm only plotting a negative y-coordinates. So -0.88, this is 1.2, and this is 0.54. So then what will this point represent? This point, -1, -0.88. Not local, but only absolute, indeed, absolute minimum. What do you think about 2, 1.2? Yes, so this is an absolute max. It happens to be a local as well, or relative. And what can you say about 4, 0.54? Nothing. That's exactly what I'm going to write, nothing. By nothing, we mean it's not a point of extrema. Well, I'm sorry, James. I thought I was giving you a present. I no longer have it. So, can you share with Tom? I'll give Tom this one at the end. Sorry about that. Okay, is this clear? So this is how we study a function on a closed interval. We're not asked to graph the function, so we don't have to worry about the second derivative or concavity or anything like that. We are only asked to find the max min, local and global, of a function on a closed interval. And we have to study what happens at the end points of the interval. Is this okay? Everyone? Okay. Are we ready for the second problem? Yes? Can we move on to the second one? Verify that the function satisfies the hypothesis of the mean value theorem on this interval, and then find all numbers that satisfy the conclusion of the mean value theorem. Okay, 1 minute. So what is the first condition or hypothesis of the mean value theorem? Yes, Tom? Yes, f is continuous on the interval -2, 2 closed as a polynomial function. Perfect. Condition number 2 or hypothesis number 2. On the open interval, yes. F is differentiable on -2, 2 for the same reason as a polynomial function. Good. There are only 2 conditions or hypotheses for the mean value theorem. Then, therefore, by MVT, at least one in the open interval -2, 2, such that f prime of c will equal, careful, that was the Rolle's theorem. So f of 2 minus f of -2 over 2 minus -2. F of b minus f of a over b minus a. It's very close. But Rolle's theorem also requires f of a equals f of b. Is that clear? So now we have to determine these values of a function f of 2 and f of -2 and put them in and find c. In the meantime, we should find f prime of x. So what is f prime of x? Very good. Perfect. How much is f of 2? And how much is f of -2? So 8 minus 6 is, yes, indeed, 4. And then -8 plus 6, I think it's 0. -8 plus 6 plus 2. Okay, 0. So then this side of f prime of c becomes 3c squared minus 3. And the other side is 4 minus 0 over 4. 2 minus -2 is 4. So then the equation we have to solve is 3c squared minus 3 equals 1. Or 3c squared equals 4. Or c squared equals 4/3. Or when I take the square root, I get c equals plus or minus 2 over the square root of 3. If both are in the interval -2, 2, which they will be, because it's a symmetric interval, then I will say both are guaranteed by the mean value theorem. But I have to show or make sure that I checked -2, 2. Is 2 over the square root of 3 in the interval -2, 2? Then both of them will be. Yes? So I'm dividing 2 by the square root of 3. And I got 1.155. So approximately 1.155. 1.155. 1.155. So yes, so in this particular situation, the function had two such numbers between -2 and 2. Any questions on this? The mean value theorem guarantees at least one, but the function may have more. Moving on to L'Hopital's rule. Any questions on this problem? So when we're asked to find the value C guaranteed by the mean value theorem, we will have to state two hypotheses: that the function is continuous and differentiable on the open interval, but continuous on the closed interval. Then we have to create that equation, f prime of x, f prime of c equals f of b minus f of a over b minus a, and solve the equation. Find c, guaranteed, make sure that it's in the interval that was given to us. Any questions on this problem? Are we okay with it? Yes? Okay. So we're moving on to problem 3, L'Hopital's rule. Yes? Right, you wanted to say something? No. Okay, so we have limit sine x multiplied by natural log x when x approaches 0 from the right. So let's work on this for a minute. Let me know if you have questions. If you need us to get it started, we can get it started together. Yes? Okay, let's get it started together. Very good. So first I see a product, right? It's a limit of a product. I need to see what's happening here, and what if the answer is 5, then I'm done, right? I still have to check and see what it is. As x approaches 0 from the right, where does this go?
0 times infinity.
0 times infinity, indeed, because remember, natural log looks like this. And this one approaches negative infinity, or negative infinity doesn't mean any. It's not a big deal, it's the same thing. So we are looking at this indeterminate case, which is not the worst, because it's not the power, it's the product. So when I see a product as an indeterminate case, I have huge chances, big chances of changing into, and what do I want to change it into?
Ratio.
Exactly. Why do I want it a ratio? Because I'm looking for, and I hope for, 0 over 0 or infinity over infinity. So that's not a big problem. Never move this anywhere. This is not a friendly function to be moved to the denominator, but this one is. So I will change limit x approaches 0 from the right, natural log at the top, and change sine into 1 over sine x. Because when I divide by a fraction, I have to flip the fraction. So I didn't change the problem, I changed the presentation of the problem. So from sine x natural log x, now I have natural log x over 1 over sine x. And I know that 1 over sine x is a trig function. Which trig function is that? Very good. So this is limit as x approaches 0 from the right, natural log x, cosecant x. It's not that I'm saying that cosecant x is a very friendly function in the sense that, you know, it's complicated when we even think of the derivative. But right now, I know for sure that this approaches infinity or negative infinity. The sign is not important, but 1 over 0 from the right is infinity. So that's all I needed for now. Why did I need this? Because now L'Hopital's rule will help me get rid of natural log. Natural log was in the way. But now differentiating top and bottom, which I can do in this way only if I have a limit, and only if I have a ratio, and only if I have infinity over infinity or 0 over 0. So then I can apply L'Hopital's rule and say limit as x approaches 0 from the right. The top prime is 1 over x. Although the denominator is not very nice, cosecant squared, cosecant prime is negative cosecant cotangent. And now I will rewrite it. In this way. Limit as x approaches 0 from the right, -1 over x. Instead of cosecant, I'm going to write 1 over sine. Instead of cotangent, I'm going to write cosine x over sine x. And now let's take it from here and think about it for a moment. And see what you're going to do to further simplify it and find the limit. Let's work on it for another minute. And then we'll finish it up together. So, of course, I'm going to multiply this and flip, because that's the best thing to do. And then apply the limits that we know for almost 2 months and a half. So how will you rewrite this? Just dictate. Limit as x approaches 0 from the right, minus in front. What do we have? Sine squared.
Sine squared x.
Very good. I'm just going to keep it as sine times sine. You'll see in a moment why. Over.
X cosine x.
Very good. This is not a big deal. Now this is really nice because I know where it's going. This one, where is this one going? As long as this piece and this piece and this piece are all the same and they go to 0, right? These, yes, and this one will be going to 1. Where does sine go when x approaches 0? Where does cosine go when x approaches 0?
1, 1.
So the answer is
Wait, where did the x come from? The bottom.
is this one, when we differentiate at the top.
Oh,
We differentiate natural log, which is 1 over x. So I would like you to think about this problem because here we did not want to continue with L'Hopital's rule because that product makes it very difficult. I wouldn't say maybe I shouldn't say very difficult, but this is not a friendly situation to apply L'Hopital's rule on this. Furthermore, there is no need, and I can't even apply L'Hopital's rule because the numerator is 1. So I have to do something else. So I wouldn't even be able to apply L'Hopital's rule. But I really don't want to, even if I can. I will not, because of that product. I have to apply the product rule. So since the numerator is 1, then I have to do something else to the denominator. Okay, any questions on this? The next one. E to the x plus x raised to 1 over x. Now I'd like you to say, for this one, I have to, because there is no other way. I have no other way. There is no formula, right? I'm not differentiating, but determining the limit for such a situation, I will have to apply log. So remember step 1, you have to denote the function by y. Can anyone tell us step 2? Apply natural log to both sides. And can anyone tell us step 3? After we apply natural log to both sides, what will be the next step?
Differentiate both sides.
Apply, we're not differentiating, it's the limit. Apply the limit operator to both sides. So step 1, denote this function by y. Step 2, apply natural log to both sides. Step 3, apply the limit to both sides. So let's work on this for a minute. So let me put you on the right track one more time. So this is y equals e to the x plus x raised to 1 over x. That would be our first step, correct? Then natural log y equals 1 over x natural log e to the x plus x. And then we apply the limit as x approaches infinity. And by the way, again, I jumped into conclusions without saying, where does this go? When x approaches infinity, this piece approaches, and this is infinity. Infinity plus infinity will be infinity, right? So then 1 over infinity is 0. So this is a power, right? One of the indeterminate cases, power. More difficult than the product. And the product is more difficult than the ratio. So the ratio is basically the easiest. And then the product, and then the power. So I have 2 steps. I have to change this into a product, and then eventually into a ratio. So we denoted y, the function by y. We applied natural log to both sides. We got this. So now the limit. So this is limit as x approaches infinity from natural log e to the x plus x divided by x. Although it looks difficult, it's really not. So we change it into a product. This stage is a product, but this product immediately changes into a ratio. So from this point moving forward should not be difficult. So what indeterminate case is this? Yes, exactly what we were hoping for, or 0 over 0. So therefore we can apply L'Hopital's rule. X approaches infinity. The top prime will be
1 over e to the x plus x times e to the x plus 1.
very good. And the denominator is 1. However, this is still okay because it's a ratio. So let's see what we have now. Limit as x approaches infinity, e to the x plus 1 over e to the x plus x. As long as it's a ratio, I either get a number or infinity, or 0 over 0 or infinity over infinity, and I can continue using L'Hopital's rule. So the top approaches perfect. The denominator approaches perfect. So I can continue. As if this is, again, a different function starting from scratch. I differentiate the top and I differentiate the denominator and I get perfect. Now still this is infinity over infinity. So this is limit x approaches infinity, e to the x over e to the x. And now I can simplify, and the limit is 1. This is good, but it's not good enough. Remember, I have to go back to the starting point and connect it to the end point. So we're going to copy the beginning. Limit as x approaches infinity from natural log y equals 1. Okay. What happens next?
We switch.
Exactly. We swap the operators. We are allowed to do that because the function we're talking about, or the natural log of the function we are talking about, is continuous. So conditions are fulfilled. So then now I have natural log of the limit as x approaches infinity of y is 1. So now I know what the limit equals to, because I know there is only one number whose natural log is 1, e. So therefore, this must be e, which means limit as x approaches infinity from The function was e to the x plus x. Everything to 1 over x is e. Any questions on this problem? Yes. But is it clear? Any questions? Would you like to summarize the steps? It's a long problem. Would you like to summarize the steps? So first I have to determine, look at the indeterminate case, and it happens to be infinity raised to 0, which is a power. I'm hoping that I can somehow change it into a product, and I'm hoping that I can change that product into a ratio, so I can apply L'Hopital's rule. So what we did as the first step, we denoted this function by y. We applied natural log to both sides. Now I change it into a product. Then we apply the limit to both sides. And we are determining the limit of something we are not asked to, but we have to. So we're not asked to find the limit of the natural log y. We're asked to find the limit of y, but we are getting there slowly. So then I apply limit to this side, and I continue. It happens to be infinity over infinity. I differentiated one. I applied L'Hopital's rule, not differentiated. I applied L'Hopital's rule once, twice, 3 times, and then I ended up with e to the x over e to the x, which is 1, so there is nothing else I can do here. Then I copy the beginning of the limit and the end, the answer. And then I realized that I was allowed to, and I can, because it's a continuous function, e to the x plus x to 1 over x. It's a continuous function. And natural log of that is also continuous, so I was allowed to swap the operators. And then at this point I say, okay, natural log of what is 1? Well, this must be e. There is no other way. So please review these steps several times and do a couple of problems. Well, we had several before this one. Okay, so now we are looking at this function, and we want to present everything. Find everything and graph it. Can anyone just give us a starting point for a function like this to graph it?
The domain has to be great.
Absolutely. We have to find the domain. That is our starting point. Thank you, Tom. Anyone needs help? Let me know when you want me to start. Okay, can we start together? Yes? Okay, so first I'm asked to graph this function, so I have a long road ahead of me, right? So I have to start with a domain in which I know that x has to be greater than or equal to 0 because the square root of x will not exist otherwise. So I know that the domain is 0 to infinity. I'll get my table going so I can summarize all the information in here. And I put 0 to infinity. That's it and nothing else. Now I want to determine everything I can about the function first. What can I determine? And behavior, x and y intercepts, that's pretty much it, right? So first of all, I will plug in 0 to get this number, and then I will find the limit here. So when I plug in 0, what do I get? Perfect. Now I want to find this. So I have to find the limit of 2 the square root of x minus x when x approaches infinity. Remember, I know I'm finished with all the information. I have all the information when the table is completely filled up with everything. You fill it out with everything you need. Okay, so now I look at these two and I ask myself, which one is the most powerful? The square root of x or x? X, because x is more powerful. This doesn't count. So when x approaches infinity, where does the function go? That's it. I already found the y-intercept because I plugged in 0 for x. But I need to find the x-intercept, and I'm done with the function. So how do I find the x-intercept for any function? Set y equal to 0. Very good. So f of x equals 0 means 2 the square root of x minus x equals 0. Now I have to step back and look at this and ask myself, what is it? Because I know so many different types of equations, but what type of equation is it? If it has a ratio and x in the denominator, I will say yes. It's a radical equation. Now I have to think, how do I solve a radical equation with one radical? I have to isolate the radical first. That's mandatory. So I isolate the radical by moving x to the other side. 2 the square root of x equals x. Good. Now what? Yes, but not yet. What do I have to do next? This is a radical equation. apply the square, yes, square both sides indeed, because I want to eliminate the square root of x. Perfect. What do I have on the left?
4x
Perfect. What do I have on the right?
squared.
Very good. Now this is quadratic. So now this is x squared minus 4x equals 0. And of course, I will factor out x. How many options? 2. X equals 0 and x equals 4. I have to check them. Why do I have to check them? Because I squared both sides, and I may have extraneous solutions. Let's check. Back in the original problem. 0, 0, yes. 4. Let's go to 4, 2. 2 times 2, 4. 4 minus 4 is 0. Both work. This one I already have in the chart. So I have to put in this. That is all I can find from the function about the function itself. There is nothing else. And I put it in the table. Now, what is my next step? After I'm done and I found the x and y intercepts and the end behavior and the limits, what do I have to find next?
Derivative.
The derivative. Perfect. So let's find f prime. So let's copy it here to the square root of x minus x. So here's f prime. What did we get for f prime? So 2 over 2 the square root of x minus 1. When we differentiate the square root of x, we have 1 over 2 the square root of x and minus 1. I'll simplify. So then I have 1 minus the square root of x over the square root of x. I have to change it into a ratio or a product if that's the case, because I'm prepping it for finding
Second derivative.
critical numbers. No, I will not. I will never differentiate this. I will always differentiate the raw one, or change this into x to negative 1/2 minus 1. Not on the ratio. Very good. So I'm prepping it for critical numbers. So now I know critical numbers come from two possible sources, from f prime of x being undefined or from f prime of x being 0. Yes, please. Paul?
How did you get to 1 minus square root of x?
When I subtract two fractions that do not have the same denominator, I have to find the least common denominator, and I multiply this one by the square root of x. Better? So, is f prime undefined? The answer is yes,
0.
at 0. So, I go back and show that. If the first derivative is undefined at 0, so will any other derivative be undefined at 0.
What was that your chapter?
F prime being undefined.
What
This
was
one,
it?
at x equals 0.
You're saying something is, there's two options for something?
For critical numbers. Critical numbers can come from two options. Either from f prime being undefined where the function is defined, and we did find one. It's at 0. The function is defined, but the derivatives are not. I'm not interested in the second derivative right now, but the first derivative is not. And also we have a critical number coming from f prime being 0. Which equation do I have to solve? For 1 minus the square root of x over the square root of x being 0? 1 minus the square root of x equals 0. What type of equation is it? Radical. So I have to do the same thing I did before. 1 equals the square root of x, and then square both sides, and I get x equals 1. But I have to make sure that it works. Yes, it does. So I go back to the table. I put 1 in the table and 0 under in the row for f prime. But I also have to determine this y coordinate right here. Mandatory. So let's go back. 2 times 1 minus 1. 1. So far, so good? So far, so good? Okay, so this is our derivative. what type of number will this be no matter what? On the domain of 0 to infinity, of course, otherwise it will not exist. Always positive. So I need to study the sign. So I'm going to plug in 0.5. 0.5 is between these two, 0.5. 1 minus the square root of 0.5. Sign. Perfect. I'm plugging in 4 now. Square root of 4 is 2. 1 minus 2. Moment of truth between row 1 and row 2. From 0 to 1, what does the function do? Is that supported by the first derivative, the sign of the first derivative? Yes. From 1 to 0, supported by the sign of the first derivative? And from 0 to negative infinity, is that supported by the sign of the first derivative? Any questions? So now let's study the second derivative and we're done. I don't want this, and I really don't want this either. So the first derivative is 1 over the square root of x minus 1. I am going to change it into something as easy as possible as x to negative 1/2 minus 1. Do not try not to complicate things. This is not what I want to differentiate. This is what I want to differentiate. So can anyone give us the second derivative then? So negative 1/2 x2 negative 1 minus 1/2 minus 1 is negative 3/2. So this is negative 1 over 2 the square root of x cubed. Is this ever 0? No, because it's a fraction, and it would be 0 only if the top could be 0. But at the top I have 1, so it will never be 0. What is the sign of all this? Remember, the domain is x greater than or equal to 0. But, of course, it's undefined at 0. What will be the sign of all this? Always positive, but there is a negative in front. So can anyone tell us the sign of the second derivative everywhere? Is there an inflection point? No. Good. Any questions? Any questions? Good, perfect. So let's graph it. All I care about is my table. I have 0, 0. I have 1, 1. And I have 2, 3, 4, 0. So here's what my table says. From 0 go to 1, from the origin go to 1, 1, increasing, opening downward. Now, all the way decreasing to negative infinity, opening downward and crossing the x-axis at 4, 0. And this is the function f of x to the square root of x minus x. So, can anyone tell us what kind of point is this, which we forgot to write here? What type of point is 1, 1? Definitely a maximum. It is a local max, but it happens that for this function is also the absolute max. So absolute max. There's no other information that you can obtain with any other device like software, computer software, or calculator. Nothing else is there out there about this function. We found everything about it. Any questions? Yes. Yes, Tom, go ahead.
We haven't really found it for symmetry in a while. It's just curious because the problem asks
For symmetry, all problems ask for symmetry because it's one of, yes, very good. Well, a function that is defined on 0 to infinity cannot be symmetric. But right? I cannot even plug in negative x for this function, but you're making a good point. So let me refresh your memory. For odd and even, for odd, we have to show that f of negative x equals the opposite of f of x. And for even, we have to show that f of negative x equals f of x. Odd means symmetric with respect to the origin. And this is the y-axis. So once the function, you have a great point. Once the function I know is defined on 0 to infinity, there is no way it can have any type of symmetry. That's why I didn't mention it, but you are correct. I should have. Thank you. Now, we did problem 5 in class, but if you want to work on it again, let's work on it again. If you say no, we'll move on and do something else. Do we want to? Yes? Let's do it? Very good. So let's work on it. 2 minutes.